What happened to thousands of advanced warplanes when Nazi Germany collapsed in May 1945? How did the Allies handle the most sophisticated air force the world had ever seen? When the Third Reich surrendered, more than 20,000 Luftwaffe aircraft remained scattered across Europe. Some hidden in forests, others abandoned on runways, and many destroyed by their own crews to prevent capture. What came next was unprecedented. A massive operation to seize, study, and ultimately decide the fate of Hitler's aerial arsenal. In this video, we will show you what happened to the Luftwaffe planes after World War II and reveal some surprising truths about how these aircraft shaped the future of aviation. On the morning of May 8, 1945, the unconditional surrender of Nazi Germany became official. Across occupied Europe, Luftwaffe pilots received orders that seemed impossible after 6 years of war. Cease all combat operations immediately, ground all aircraft, and await Allied instructions. For many airmen, this moment brought relief, mixed with uncertainty. Some had been flying obsolete aircraft against overwhelming odds for months. Others piloted the most advanced jets and rockets ever built, machines that represented the cutting edge of aeronautical engineering. Now, all of them faced an unknown future. The scale of what the Allies discovered was staggering. Intelligence reports had tracked Luftwaffe strength throughout the war, but nothing prepared the occupation forces for what they found in the weeks following surrender. On airfields across Germany, Austria, and occupied territories, thousands of aircraft sat in various states of readiness. At Flensburg in northern Germany, more than 200 aircraft crowded the tarmac. At airfields in Bavaria, Messerschmitt factories had continued production until the final days, leaving dozens of incomplete fighters on assembly lines. In underground facilities carved into mountainsides, the Allies found jet engines, experimental designs, and technical documents that would influence aviation for decades. The immediate challenge was preventing destruction. German orders had been clear: no advanced technology should fall into enemy hands. As Allied forces advanced through Germany in the war's final weeks, Luftwaffe ground crews received instructions to destroy aircraft rather than allow their capture. Many complied. Across hundreds of airfields, mechanics set fires, removed critical components, or simply abandoned planes where they stood. At Rechlin, the Luftwaffe's primary testing facility, engineers attempted to burn technical documents and prototype aircraft before Soviet forces arrived. Some succeeded, others ran out of time. However, the Allies moved quickly. Special intelligence units, known as technical intelligence teams, had prepared for this moment. These groups consisted of pilots, engineers, and intelligence officers trained to identify and secure valuable aircraft and technology. They fanned out across Germany with specific lists of targets: jet fighters, rocket-powered interceptors, advanced bombers, and any aircraft incorporating new technologies. Their mission was urgent. The race was not just against time, but against other Allied powers. The United States, Britain, France, and the Soviet Union all wanted access to German aviation secrets. Lieutenant Colonel Howard Wilson led one such American team into Bavaria in late April 1945. His unit arrived at the Messerschmitt facility at Oberammergau just hours after German personnel had fled. Inside the factory buildings, Wilson's team found an aviation treasure trove. On the assembly floor sat 3 nearly complete Me-262s, their distinctive swept-wing silhouettes instantly recognizable. In adjacent hangars, they discovered components for dozens more aircraft, along with complete sets of technical drawings and production manuals. Perhaps most valuable were the wind tunnel, test results, and aerodynamic data that documented years of research. Wilson immediately posted guards and called for additional security. This facility alone would yield intelligence worth its weight in gold. The Messerschmitt Me-262, the world's first operational jet fighter, became an immediate priority across all Allied forces. When British troops reached airfields in northern Germany, they found dozens of these aircraft. Some had been deliberately damaged by retreating German crews. Others remained intact, their turbojets still functional. At Schleswig Airfield, RAF personnel discovered a Me-262 that had been hidden in a forest, camouflaged with branches and foliage. The aircraft was in perfect condition, fully fueled and armed. Its pilot had simply walked away, perhaps hoping to return someday, or perhaps accepting that the war was truly over. The Me-262 represented a quantum leap in fighter design. With a top speed exceeding 540 miles per hour, it could outrun any Allied propeller-driven fighter by more than 100 miles per hour. Its twin Junkers Jumo 004 engines marked a revolutionary departure from conventional aviation. Yet despite its advanced design, the Me-262 had suffered from chronic reliability problems, fuel shortages, and rushed production. The engines in particular proved temperamental. They required careful throttle handling to avoid compressor stalls. Their operational life was measured in just 10 to 25 hours between major overhauls, compared to hundreds of hours for Allied piston engines. Now, these aircraft would serve a different purpose, teaching the victors how jet propulsion worked and revealing both its potential and its pitfalls. Captain Eric Brown, a British Royal Navy test pilot, was among the first Allied airmen to fly captured German jets. On May 10, 1945, just 2 days after Germany's surrender, Brown climbed into a Me-262 at Lechfeld Airfield in Bavaria. The experience would become legendary in aviation history. Brown later recalled in vivid detail how different the jet felt from anything he had previously flown. There was no propeller vibration, no torque to compensate for. The acceleration was unlike anything he had experienced in propeller aircraft, smooth, relentless, almost eerie in its quietness compared to the roar of piston engines. As Brown advanced the throttles, the Me-262 leaped forward. Within seconds, he was traveling faster than he had ever flown. The jet's responsiveness surprised him, though he noted the engines required careful handling. Rapid throttle movements could cause them to flame out, leaving the pilot powerless. Brown discovered this limitation himself during subsequent flights when aggressive maneuvering caused one engine to quit. He managed to restart it, but the experience taught him respect for the aircraft's temperamental nature. Brown would eventually fly more than 50 different captured German aircraft types, including nearly every variant of the Me-262. His reports would prove invaluable to Allied aviation programs, providing not just technical data, but pilot perspectives on what these aircraft were like to actually operate. He documented everything: the excellent visibility from the cockpit, the sensitive controls at high speed, the poor low-speed handling, and the dangerously long takeoff and landing rolls that left the aircraft vulnerable to attack. The United States Army Air Forces established Operation Lusty, an acronym for Luftwaffe Secret Technology, to systematically collect German aircraft. Colonel Harold Watson led the operation, which prioritized identifying, securing, and shipping valuable aircraft back to the United States for detailed analysis. Watson's team worked with extraordinary speed and precision. Within weeks of Germany's surrender, they had identified over 300 high-priority aircraft. These ranged from the Me-262 and the rocket-powered Me-163 to advanced bombers like the Arado R-234 and reconnaissance planes featuring cutting-edge camera equipment. The logistics were immense and complicated. Transporting aircraft across war-torn Europe to ports required coordination between multiple military branches. Roads and railways had been heavily damaged by years of bombing and combat. Bridges were destroyed. Fuel was scarce. Nevertheless, Watson's team improvised solutions. Some aircraft were flown directly to collection points when pilots could be found who were willing to risk flying unfamiliar German planes. Others were disassembled for transport by truck or rail. The smallest aircraft were loaded whole onto trucks. Larger types required partial disassembly, their wings removed and fuselages transported separately. At Cherbourg, France, Allied forces converted the port into a massive staging area for captured aircraft. The harbour, which had been crucial to the Normandy invasion, now served a different purpose. Engineers disassembled larger planes in specially designated areas near the docks, carefully labelling each component for reassembly in the United States. Mechanics catalogued every bolt, wire, and panel. Nothing could be left to chance. These aircraft would need to be perfectly reconstructed thousands of miles away by American technicians who might have no direct experience with German engineering practices. Smaller aircraft were loaded intact into cargo holds of Liberty ships returning from Europe. Each ship carried a bizarre cargo, Me-262s, secured alongside Focke-Wulf FW-190As. Experimental jets sharing space with conventional fighters, bombers alongside reconnaissance planes. Between June and September 1945, convoy after convoy departed Cherbourg carrying German aviation technology. Each ship represented years of research that American engineers could now study at their leisure without the pressure of combat or the restrictions of wartime secrecy. Among the aircraft shipped were at least 12 Me-262 fighters, carefully selected to represent different production variants. The Americans wanted to understand how the aircraft had evolved during its brief operational career. They also secured 3 Me-163 rocket interceptors, including one that had never been flown. Several examples of the Heinkel He-162. Salamander, Germany's cheap-to-produce jet fighter built largely from wood, made the journey. So did multiple Arado R-234s, examples of the Dornier Du 335, and even some prototypes that existed in only single examples. Britain launched its own collection effort, though on a smaller scale than the American operation. The Royal Aircraft Establishment at Farnborough became the centre of British efforts to understand German aviation technology. Ray teams secured aircraft directly from German airfields, transporting them to Britain by air whenever possible. The British were particularly interested in jet engine technology. Germany's turbojet designs were years ahead of British efforts, and understanding them could accelerate Britain's own jet programs. Wing Commander Roland Beaumont, a distinguished RAF test pilot who had flown Typhoons and Tempests during the war, was assigned to evaluate captured German aircraft at Farnborough. His reports complemented Brown's work, providing multiple perspectives on the same aircraft. Beaumont was particularly impressed by the Me-262's potential, though like Brown, he noted its operational limitations. In one report, Beaumont wrote that the Me-262 represented the future of air combat, but a future that Germany had reached too soon, without the industrial capacity to fully exploit it. Several Me-262s reached Farnborough along with examples of the Arado R-234, Germany's jet, bomber. The R-234 represented another significant achievement. As the world's first operational jet bomber, it could reach speeds approaching 460 miles per hour, making interception extremely difficult. The Luftwaffe had deployed it primarily in reconnaissance roles late in the war, using its speed to photograph Allied positions with minimal risk. At war's end, approximately 30 R-234s remained intact or repairable. The Allies seized most of them, recognizing their significance. The aircraft's twin WW2 engines and clean aerodynamic design impressed Allied engineers, who recognized its potential influence on future bomber development. The R-234's pressurized cabin allowed high-altitude operations, and its glazed nose provided excellent visibility for the bombardier navigator. British test pilots who flew captured examples praised its handling qualities and noted that it was surprisingly pleasant to fly for such a large aircraft. However, they also identified weaknesses: limited range, modest bomb load, and vulnerability to fighter attack once located. Still, the aircraft proved that jet bombers were practical, opening Allied engineers' eyes to new possibilities. However, not all discoveries were about jets. The Focke-Wulf Tar 152, an advanced propeller-driven fighter, showed how far conventional aircraft design had evolved by war's end. This aircraft represented the ultimate development of the piston-engine fighter concept. With its powerful Junkers Jumo 213 engine producing over 2,000 horsepower and its high-altitude performance capabilities, the TR-152 could compete with late-war Allied fighters on roughly equal terms. Some German pilots considered it the finest aircraft they had ever flown. Only a few dozen TAR-152s had entered service before the war ended, but those that survived captured Allied attention when American forces overran the Focke-Wulf factory at Cottbus. They found several TAR-152s in various states of completion. One was immediately secured for shipment to the United States. Test pilots at Wright Field who later flew this aircraft praised its handling characteristics and combat potential. The consensus was that had Germany produced it in larger numbers earlier, perhaps in 1943 instead of 1944, the air war might have developed differently. The TAR-152 could have challenged Allied fighters more effectively than the aging Bf-109 and early FW-190 variants that formed the Luftwaffe's backbone for much of the war. The Soviet Union pursued German technology with particular intensity and different methods than their Western allies. As Soviet forces swept across Eastern Germany in the war's final months, they secured numerous Luftwaffe facilities before Western allies could reach them. At Oranienburg, north of Berlin, Soviet forces captured documents and equipment related to jet engine development. At the BMW factory in Basdorf, they found complete engine production lines. Soviet engineers immediately began cataloguing everything, preparing to ship valuable equipment back to the USSR. Stalin himself took personal interest in German aviation technology. The Soviet leader understood that jet aircraft represented the future of air combat, and he was determined that the Soviet Union would not fall behind. In June 1945, he ordered the creation of special bureaus to study captured aircraft and integrate German innovations into Soviet designs. Thousands of German engineers and technicians were identified through systematic searches of personnel records. Many were persuaded or compelled to continue their work, now serving Soviet interests rather than German. The treatment of these German specialists varied. Some were offered relatively comfortable positions in Soviet design bureaus, receiving decent housing and working conditions in exchange for their expertise. Others faced harsher circumstances, particularly those suspected of war crimes or those who resisted cooperation. The Soviet approach was practical rather than ideological. Expertise was valuable regardless of its source, and the Cold War was already beginning even before the Hot War had fully ended. France also claimed a share of captured aircraft, though French efforts focused more on rebuilding their shattered aviation industry than on advanced research. French forces secured several airfields in southwestern Germany and Austria, finding aircraft including Messerschmitt Bf-109s, Focke-Wulf Fw-190As, and even a few Heinkel He-177s. These conventional fighters and bombers, though obsolete by late war standards, still possessed value. France had a practical need. Their own aircraft industry had been devastated by 4 years of occupation and Allied bombing. French military aviation had to be rebuilt almost from scratch. Using captured German aircraft as interim equipment made sense, and studying them could inform French designs. Several captured Bf-109s were pressed into service with French squadrons, where they served for several years. The irony was not lost on French pilots, many of whom had fought against these same aircraft types just months earlier. The fate of individual aircraft varied dramatically based on their type, condition, and the priorities of the capturing nation. Some became museum pieces almost immediately, recognized as historically significant even before testing began. Others underwent extensive flight testing that lasted years. Still others were deliberately destroyed after examination, particularly common types that offered little unique information. The decision of what to preserve and what to eliminate often came down to practical considerations. How unique was the design? How much could be learned from it? And how many examples existed? Common types like the Messerschmitt Bf-109, of which thousands remained scattered across Europe, received less attention than rare prototypes or advanced designs produced in small numbers. The Bf-109 had been extensively studied throughout the war. Allied forces had captured examples as early as 1940, when one landed by mistake in Britain. By war's end, the type held few secrets. While some examples were saved for museum display or comparison testing, most were simply scrapped. Their aluminum was salvaged and recycled, turning German fighters into pots, pans, and building materials for war-torn Europe. Among the most fascinating discoveries were Germany's experimental aircraft, planes that had never entered full production but represented radical departures from conventional design. These were the aircraft that most excited Allied intelligence officers and engineers. They showed not just what Germany had achieved, but where German thinking was heading. The Horten-Ho 229, a flying-wing jet fighter, exemplified this category. Designed by brothers Reimar and Walter Horten, this aircraft featured no conventional fuselage or tail. Instead, its entire structure formed a single wing with engines embedded within. When American forces discovered a nearly complete prototype of the Ho 229 at Friedrichsruhe in April 1945, they immediately recognized its significance. The aircraft sat in a workshop, lacking only final assembly and testing. American engineers photographed it from every angle, measured every dimension, and documented every detail. Then, they carefully disassembled it for shipment to the United States. This aircraft represented a vision of aviation's future, one that would not fully materialize until decades later with the development of stealth aircraft. Modern analysts have noted that the Ho 229's wooden construction and smooth surfaces would have given it some stealth. Characteristics, though whether the Horten brothers intended this is debatable. The Backenbach 349 Natter offered another glimpse into German desperation and innovation in equal measure. This rocket-powered interceptor was designed for point defense against Allied bomber formations. The concept was radical and, frankly, terrifying. Pilots would launch vertically from rails, guided by ground controllers during the ascent. At altitude, they would intercept bomber formations, fire unguided rockets at the bombers, then eject and parachute to safety while the aircraft itself crashed. The Natter was essentially expendable, designed to be cheap and quick to produce rather than reusable or sophisticated. The concept was born of desperation. By late 1944, Germany was losing hundreds of pilots and aircraft to Allied air superiority. Conventional fighters could not be produced quickly enough or in sufficient numbers to counter Allied bomber streams. The Natter represented an attempt to solve this problem through radical simplification. It required minimal training to operate, the pilot barely controlled it during ascent. It could be built rapidly using simple materials and non-critical resources. It could be launched from any suitable site, not requiring airfields that Allied bombers had systematically destroyed. Test flights had resulted in at least one pilot death. On March 1, 1945, test pilot Lothar Sieber climbed into a Natter for the first manned vertical launch. The rocket fired, and the aircraft shot skyward at tremendous acceleration. But something went wrong. Observers on the ground watched in horror as the aircraft's canopy separated prematurely at high altitude. The Natter continued upward, now pilotless, before falling back to Earth and disintegrating on impact. Sieber's body was found in the wreckage. He had not managed to eject. The program continued nevertheless, with additional test flights scheduled. Several production Natters were built, 36 according to records, but none ever saw operational use. When American forces overran the testing site at Kirchheim unter Teck in April 1945, they found multiple Natters in storage, along with launching equipment and technical documentation. The Americans were simultaneously impressed and appalled. Impressed by the innovative engineering that made vertical rocket launch practical, appalled by the desperation that would create such a dangerous system and ask pilots to fly it in combat. Nevertheless, the Allies studied the Natter carefully. Its vertical launch system and rocket motor offered insights that would prove valuable for missile development. The Americans shipped several Natters back to Wright Field, where they were examined in detail. American engineers recognized that while the Natter was unsuitable as a piloted aircraft, many of its concepts could apply to guided missiles. The line between aircraft and missile was already blurring, and the Natter represented an intermediate form that pointed toward future developments in surface-to-air missile systems. Meanwhile, on airfields across occupied Germany, thousands of conventional Luftwaffe aircraft awaited decisions on their fate. Messerschmitt Bf-109s and Focke-Wulf FBU-190As, the workhorses of the Luftwaffe throughout the war, sat in long rows stretching as far as the eye could see. At Fürth Airfield near Nuremberg, American troops counted more than 300 Bf-109s parked wing to wing. Many were battle damaged, showing bullet holes, patch repairs, and the wear of years in combat operations. Others had been cannibalized for parts by desperate German mechanics trying to keep a dwindling number of aircraft flying. Still others remained in flying condition, fully fueled and armed, as if their pilots might return at any moment to take them into battle once more. What should be done with them? The Allies had no need for thousands of obsolete German fighters. Propeller-driven aircraft were already becoming outdated as the jet age dawned. Storing them made no sense when precious resources were needed for reconstruction, yet destroying them outright seemed wasteful, and some officers argued that at least representative samples should be preserved for study or historical purposes. The decision-making process occurred at multiple levels, from individual unit commanders making snap judgments to high-level policy decisions in Washington, London, and Moscow. The solution came in phases. First, intelligence teams selected examples of each aircraft type for detailed study. These would be transported to testing facilities in the United States, Britain, and the Soviet Union. Selection criteria included condition, variant type, and production series. Engineers wanted to understand how German aircraft had evolved over the war years. An early production Bf-109E from 1940 held different lessons than a late production Bf-109K from 1945. Both were valuable for different reasons. Second, certain aircraft were allocated to Allied air forces for evaluation and training purposes. American fighter pilots wanted to fly captured German fighters to understand their capabilities and limitations. This knowledge could inform tactics and training programs. British pilots had similar interests. French forces, rebuilding their air force, saw practical utility in using captured aircraft as interim equipment. These aircraft received maintenance and were kept airworthy, at least temporarily. Finally, the vast majority would be scrapped. Between June 1945 and late 1946, thousands of German aircraft were methodically destroyed. The process was systematic but sobering. At some airfields, ground crews used bulldozers to push planes into massive piles before burning them. The fires burned for days, sending columns of black smoke into the German sky. At other locations, aircraft were cut apart with torches, their aluminum salvaged for other purposes. Engines were removed and either studied or melted down. Instruments were harvested for examination. Everything else became scrap metal. At Flensburg, a specially designated demolition site in northern Germany, hundreds of aircraft met their end in a carefully orchestrated operation that took place over several days in late May 1945. Photographs from the period show surreal scenes: rows of Bf-109s, their wings removed, fuselages stacked like cordwood awaiting destruction. WW190As with their distinctive radial engines pointed skyward. Heinkel, her 111s, twin-engine bombers that had terrorized Britain in 1940, now rendered powerless. It was an ignominious end for machines that had once represented the cutting edge of military technology and had played crucial roles in one of history's most destructive conflicts. Yet even as thousands of aircraft were destroyed, the most valuable examples were carefully preserved and protected. In the United States, Wright Field in Ohio became the primary destination for captured German aircraft. The facility, which would later be renamed Wright-Patterson Air Force Base, had extensive testing facilities and a staff of experienced engineers and test pilots. By late 1945, the facility housed an extraordinary collection: Me-262s, Me-163s, He-162s, R-234s, Do-335s, Tar-152s, and dozens of other types. The variety was astounding, representing virtually every significant German aircraft development from the war years. American test pilots flew them extensively, documenting performance characteristics and comparing them to American designs. These tests revealed both the strengths and weaknesses of German aviation technology. The pilots completed detailed evaluation forms for each aircraft, noting speed, climb rate, maneuverability, visibility, control response, and dozens of other parameters. They assessed combat potential, ease of maintenance, pilot workload, and operational suitability. The resulting reports filled volumes and provided invaluable information for American aircraft designers. Major Frederick Borsodi, an experienced P-47 pilot, flew multiple captured German fighters at Wright Field. His reports on the FW-190A were particularly insightful. He noted that the aircraft's BMW radial engine provided excellent power and reliability. The cockpit layout was logical and well designed. Visibility was good in most directions. However, the control forces were heavy at high speed, making rapid maneuvering exhausting. The aircraft lacked some of the refinements American fighters possessed, such as powered controls or sophisticated gun sights. Nevertheless, Borsodi concluded that the FW-190A was a formidable opponent that American pilots had been right to respect. Captain Brown, meanwhile, continued his systematic evaluation of captured aircraft in Britain. His test reports remain remarkably detailed, combining technical observations with pilot perspectives that bring the aircraft to life. On the Me-262, he noted excellent speed and climb rate, but criticized poor engine reliability and limited ammunition capacity. The aircraft carried only 100 rounds per gun, enough for perhaps 3 seconds of firing. This forced pilots to be extremely judicious with their ammunition, a significant tactical limitation. On the Heinkel He-162 Salamander, Germany's cheap-to-produce jet fighter built largely from wood, Brown found surprisingly good flying characteristics despite the aircraft's crude construction. The wood construction actually provided some advantages. It was easy to repair and required minimal strategic materials. The aircraft handled reasonably well and possessed adequate performance for point defense missions. However, its limited range of only 90 minutes of flight time, poor armament, and lack of sophistication made it unsuitable for offensive operations. Brown concluded that the He-162 represented an intelligent design, given Germany's circumstances, but it was ultimately a compromise born of desperation rather than a first-line fighter design. The Messerschmitt. Me-163 Comet, a rocket-powered interceptor, proved particularly challenging and dangerous to evaluate. with a powered endurance of less than 8 minutes and a volatile fuel mixture that could explode on impact. The Me-163 was one of the most dangerous aircraft ever built. German pilots had suffered numerous casualties while flying it. The fuel, a mixture of concentrated hydrogen peroxide and hydrazine known as C-Stoff and T-Stoff, was extraordinarily corrosive and toxic. It could dissolve human flesh on contact. Ground crews working with it required extensive safety equipment and training. Allied test pilots approached the Me-163 with extreme caution. Only a handful of flights were conducted, each meticulously planned and briefed. The pilots who flew it reported an extraordinary experience. The Walter rocket motor generated tremendous thrust, accelerating the aircraft at a rate unmatched by any propeller or jet aircraft. The climb rate was phenomenal. The Me-163 could reach 30,000 feet in less than 3 minutes. However, the powered flight time was brutally short. After 8 minutes, the fuel was exhausted and the aircraft became a glider. Pilots had to judge their attack runs carefully and plan their glide path back to the airfield. The Me-163 reached speeds exceeding 600 miles per hour in level flight, faster than any other aircraft of its era. Yet its operational limitations rendered it more of a technological curiosity than a practical military weapon. The fuel was too dangerous to handle routinely. The endurance was too short for effective combat operations. The landing was treacherous. The aircraft's skid landing gear on grass or dirt runways meant that any slight error could result in the aircraft tumbling and the volatile fuel exploding. Several German pilots had died this way. Allied test pilots, after experiencing the Me-163 firsthand, concluded that while it demonstrated what rocket propulsion could achieve, it was fundamentally unsuitable for operational service as designed. German helicopter development also attracted Allied attention, though helicopters were still in their infancy as a technology. The Fokker Achillesfer Tu-23 Drach, though not widely produced, represented one of the first practical military helicopters. The German military had used it for reconnaissance, liaison and rescue missions, particularly on the Eastern Front, where its ability to operate from unprepared areas proved valuable. Several examples survived the war, and the Allies studied them carefully. The United States was particularly interested in helicopter technology, as American helicopter development was still in its early stages. Igor Sikorsky had pioneered American helicopters, but his designs were still being refined. German helicopters offered alternative approaches to solving the complex problems of rotary wing flight. Some captured FAR Tu-23s were shipped to the United States, where they were examined by American helicopter manufacturers. The Sikorsky Company, among others, benefited from examining German helicopter technology, though American designs would ultimately take different evolutionary paths. As summer 1945 progressed, the massive task of sorting through Germany's aviation legacy continued at an accelerating pace. Intelligence officers compiled comprehensive reports on production facilities, design bureaus, and research programs. They interviewed German engineers and pilots at length, documenting both successes and failures with equal interest. The picture that emerged was complex and nuanced. Germany had achieved remarkable technological advances, particularly in jet and rocket propulsion, aerodynamics, and high-speed flight research. However, these advances had come at enormous cost, often diverting resources from more practical weapon systems. The Me-262, for instance, consumed vast amounts of scarce materials and skilled labor to produce. Each aircraft required strategic materials that Germany lacked in sufficient quantities. Skilled workers were needed for critical manufacturing steps, yet Germany's labor force was depleted by military casualties and the demands of other war industries. The result was an aircraft that was advanced but difficult to produce in the numbers needed to make a decisive impact. Even when production accelerated in early 1945, chronic fuel shortages limited operational deployment. Advanced technology meant little when aircraft could not be fueled or flown. At Oberhammergau in Bavaria, American forces discovered extensive documentation from Messerschmitt's design bureau. Technical drawings filled entire rooms, stacked floor to ceiling. Wind tunnel test results documented thousands of hours of research. Production records showed exactly how many of each aircraft type had been built, where they had been delivered, and what problems had been encountered. Translating and analyzing these documents would take years, but the information proved invaluable. American engineers learned not just what Germany had built, but why certain design choices were made, what problems were encountered during development, and how those problems were solved or remained unresolved. The wind tunnel data was particularly valuable. Germany had invested heavily in aerodynamic research, building some of the world's most advanced wind tunnel facilities. The data from these tests provided insights into high-speed flight that would have taken Allied researchers years to develop independently. American engineers studying this data gained immediate understanding of phenomena like compressibility effects, shockwave formation, and transonic drag rise. This knowledge accelerated American research into supersonic flight by years, perhaps even a decade. The arrival of German aircraft in the United States marked the beginning of an intensive research program that would last for years. At Freeman Field in Indiana, later redesignated Wright Field in Ohio, a dedicated facility was established to house and test captured aircraft. By late 1945, the collection had grown to include over 40 different aircraft types. Engineers designated each with a foreign equipment number, known as FE numbers. The Me-262 became FE-4000. The R-234 became FE-10010. This systematic cataloguing reflected the scale and seriousness of the American effort. Colonel Harold Watson's team at Wright Field worked methodically through the collection. Each aircraft underwent ground inspection first. Engineers examined structures, systems, and components, documenting construction techniques and materials. Many were surprised by what they found. German aircraft often used different approaches to solving engineering problems. Where American designers favored certain materials or methods, Germans had developed alternatives born of different industrial circumstances and design philosophies. These differences offered valuable insights. Flight testing came next, though not without challenges. Many captured aircraft had suffered damage during transport or required maintenance after months of neglect. Obtaining proper fuel for German jet engines proved difficult, as they required specific grades not readily available in the United States. Spare parts were non-existent for many types. American mechanics learned to improvise, fabricating replacements or cannibalizing parts from multiple airframes. Despite these obstacles, test programs proceeded. The Messerschmitt Me-262 underwent perhaps the most extensive testing of any captured aircraft. Multiple examples were flown by different pilots, each providing observations. The consensus was clear: the Me-262 represented a genuine breakthrough in fighter design. Its speed advantage over propeller aircraft was decisive. However, the Jumo 004 engines were temperamental, prone to flameouts if throttle inputs were too aggressive. Engine life was measured in hours, not the hundreds of hours American engines achieved. Fuel consumption was prodigious. Still, the aircraft demonstrated what jet propulsion could achieve. American engineers took particular interest in the Me-262's wing sweep. The aircraft's wings were swept back at 18.5 degrees, a design feature that reduced drag at high speeds, while Germans had adopted wing sweep for practical reasons related to the aircraft's center of gravity. American researchers recognized its implications for transonic and supersonic flight. This insight would influence the design of American swept-wing jets in the coming years. The North American F-86 Sabre, one of America's first swept-wing fighters, owed a conceptual debt to the Me-262. The Arado R-234 bomber also received extensive evaluation. American test pilots were impressed by its performance but noted limitations. The aircraft's range was insufficient for strategic bombing missions. Its bomb load was modest, yet as a high-speed reconnaissance platform, it excelled. The United States had nothing comparable at war's end. American jet development had focused on fighters, not bombers. The R-234 showed what was possible and highlighted gaps in American capabilities. Captain Eric Brown's work in Britain paralleled American efforts, though with fewer resources. The Royal Chasseur aircraft establishment at Farnborough became home to multiple captured aircraft. Brown flew them extensively, producing detailed reports that remain valuable historical documents. His assessment of the Heinkel He-162 Volksjäger, known as the Salamander, was particularly interesting. This aircraft had been designed as a cheap, mass-producible jet fighter using wood construction and simplified systems. Brown found it surprisingly pleasant to fly despite its crude construction. It handled well and possessed adequate performance for point defense. However, he noted that its limited range and armament made it unsuitable for offensive operations. The WW2 335, Germany's twin-engine jet night fighter, impressed British evaluators with its sophisticated radar and weapon systems. The aircraft featured nose-mounted radar, oblique firing cannon, and advanced navigation equipment. While its speed was not exceptional compared to single-engine jets, it represented a complete weapon system designed for specific missions. British night fighter development had followed different paths, and the WW2 335 offered alternative approaches worth studying. Soviet evaluation of captured aircraft took a different form. Rather than extensive flight testing, Soviet engineers focused on detailed technical analysis and reverse engineering. At facilities near Moscow, German aircraft were disassembled completely. Every component was measured, photographed, and documented. Soviet design bureaus received this information with instructions to incorporate useful features into new Soviet designs. The Yakovlev Design Bureau, for instance, examined captured Mi-262s closely when developing the Yak-15, one of the Soviet Union's first jet fighters. Soviet acquisition of German technology extended beyond aircraft. The capture of BMW and Junkers engine factories provided the Soviet Union with jet engine manufacturing capability. German engineers were compelled to continue work, now producing engines for Soviet aircraft. This arrangement proved highly advantageous for the Soviet Union, which had lagged in jet propulsion development. Within a few years, Soviet jet fighters powered by German-derived engines would face American aircraft in the skies over Korea. Operation Paperclip, the American program to recruit German scientists and engineers, had significant aviation components. Dozens of aircraft designers, aerodynamicists, and propulsion experts were brought to the United States. Their knowledge supplemented what could be learned from captured hardware. Among those recruited was Alexander Lippisch, designer of the Mi-163 rocket fighter and pioneer of delta wing aircraft. Lippisch would contribute to American supersonic research programs. His work influenced designs ranging from experimental research aircraft to operational fighters. Werner von Braun, though primarily known for rocket development, also contributed to aviation technology. The V2 rocket program he had led incorporated aerodynamic principles applicable to high-speed aircraft. Von Braun and his team, now working for the United States, provided insights that accelerated American missile and high-speed aircraft programs. The line between rocketry and aviation often blurred in discussions of future technology. Not all captured aircraft survived long enough for extensive testing. Accidents occurred. On July 7, 1946, a Mi-262 being tested at Wright Field crashed during landing, killing the pilot. The aircraft's landing gear had collapsed, a known weakness of the design. Investigations revealed that while the Mi-262 possessed excellent performance, its landing characteristics required careful handling. This information was incorporated into training materials and influenced future landing gear design. The Heinkel He-178, the world's first jet aircraft to fly, survived. The war as a static display piece. Though primitive by 1945 standards, it held historical significance as the aircraft that had inaugurated the jet age on August 27, 1939. After examination by Allied experts, it was placed in storage. Its fate would remain uncertain for decades, with some sources indicating it was destroyed, others suggesting it survived. The ambiguity surrounding this historically important aircraft reflects the chaos of the immediate post-war period. France's approach to captured aircraft differed from other allies. With limited resources for testing programs, France focused on aircraft that could be quickly put to use. Several captured German trainers were incorporated into French flight schools. More advanced types were studied, but not extensively flown. French engineers were particularly interested in jet engine technology, as France had made limited progress in this area during the war. German engines and documentation provided a foundation for French post-war jet development. The disposition of aircraft varied by type and location. Some experimental aircraft existing in single examples were carefully preserved. Others, represented by dozens or hundreds of specimens, received less careful treatment. The Focke-Wulf FW-190A, once the backbone of Luftwaffe fighter forces, had become obsolete by war's end. Hundreds remained in Allied hands. Most were scrapped. A handful were kept for flight demonstrations or museum display. The decision often came down to practical considerations. Was there space to store it, resources to maintain it, and justification for preserving it? Germany's jet and rocket research had been extensive, but not all programs reached fruition. the Allies discovered drawings and models of aircraft that never flew, advanced bombers, supersonic fighters, and radical designs that pushed the boundaries of imagination. Some were practical concepts that simply ran out of time. Others were fever dreams born of desperation. American and British engineers studied these paper projects with interest, separating realistic designs from fantasy. Several concepts would resurface years later in Allied aircraft programs. The Horton-Ho Tu-29 flying wing generated particular fascination. Only one prototype had approached completion before war's end. American forces captured it at Friedrichsruhe and shipped it to the United States. At Wright Field, engineers examined its wooden construction and unusual configuration. The lack of a conventional fuselage reduced drag, while the flying wing design promised excellent range. However, control issues plagued flying wings, a problem that would not be fully solved for decades. The Ho Tu-29's influence would be seen in later American flying wing projects, including the Northrop YB-49 and, much later, the B-2 stealth bomber. Jet engine technology transfer proved as important as aircraft transfers. The Junkers Jumo 004 and BMW 003 engines represented years of development. American companies including General Electric and Pratt & Whitney studied these engines extensively. While American jet engine programs were already underway, German engines provided validation of certain design approaches and highlighted alternative solutions to technical challenges. The centrifugal flow turbojet, favoured by Germans for some applications, offered different trade-offs than the axial flow designs Americans were developing. Understanding both approaches enriched American engine development. The British experience with German engines followed similar patterns. Rolls-Royce, Britain's premier engine manufacturer, examined German turbojets with great interest. While British engine development was sophisticated, German engines offered different perspectives on materials, cooling, and combustion chamber design. Some British engines incorporated lessons learned from captured German technology, though British designers were careful to claim that their work was independent. The reality was more complex. Technological development rarely occurs in isolation, and ideas flow freely once barriers fall. Testing programs revealed not just what German aircraft could do, but what they could not. The Me-163 Comet, despite its impressive speed, proved impractical for routine operations. Its volatile fuel mixture of concentrated hydrogen peroxide and hydrazine was extraordinarily dangerous. Several German pilots had died when their aircraft exploded on landing. Allied test pilots approached the Me-163 with understandable caution. Limited test flights confirmed its performance, but also its fundamental unsuitability as a practical weapons system. The lesson was clear. Raw performance meant little if an aircraft was too dangerous or too limited to use effectively. German aircraft also revealed limitations in reliability and maintainability. Allied aircraft were designed for ease of maintenance with accessible components and standardized parts. German aircraft, particularly late-war jets, often prioritized performance over practicality. Engines required frequent overhauls. Systems were complex and prone to failure. Ground crews needed extensive training to maintain them. These limitations would not have mattered if Germany had won quickly, as designers had expected. In a protracted war, they proved critical weaknesses. The Messerschmitt Me-323, a jet-powered flying wing designed for high-speed reconnaissance, exemplified both German innovation and its limitations. One nearly complete example was captured by American forces. Its design was radical, incorporating features that would not become common for decades. Yet, it had never flown. The aircraft existed only as a testament to what might have been. American engineers examined it with interest, but recognized that it represented a path not taken, an experiment that had run out of time. As 1946 progressed, the urgency of aircraft testing diminished. Initial evaluations were complete. The most valuable insights had been extracted. Attention shifted from capture and testing to integration and application. How would captured German technology influence Allied aircraft design? The answers would emerge gradually over the following years as new American, British, and Soviet aircraft incorporated lessons learned from German planes. Some captured aircraft found unexpected second lives. The Swiss Air Force, neutral during the war, purchased several Bf-109G models from France in 1946. Switzerland had operated Bf-109s during the war. having acquired them from Germany before the conflict. Adding captured aircraft to their fleet made practical sense. The Swiss would continue flying Bf-109s until 1949, making Switzerland one of the last nations to operate the type in first-line service. Czechoslovakia also put captured German aircraft to use. Czech factories had produced aircraft for Germany during the occupation, including the Bf-109. After liberation, these factories continued production briefly, now building aircraft for the Czech Air Force. The Czech-built Avia S-99, essentially a Bf-109 with a different engine, remained in service into the 1950s. Some were even exported to Israel, where they saw combat in the 1948 Arab-Israeli War. Thus, aircraft designed for the Luftwaffe ended up serving the nation it had sought to establish. The ultimate fate of most captured Luftwaffe aircraft was destruction. Whether through scrapping programs, accidents, or simple neglect, the vast majority did not survive long past war's end. The aircraft that did survive often did so through accident or oversight, rather than deliberate preservation. Museums recognize the historical value of some types, but systematic preservation. Efforts were rare in the immediate post-war years. Money was scarce, priorities lay elsewhere, and the desire to move on from the war was strong. By 1948, most testing programs had concluded. The aircraft that remained in Allied hands were either in museums, being used for specialized research, or awaiting final disposition. The knowledge extracted from them had already been applied. American jet fighters entering service incorporated swept wings, improved aerodynamics, and engine technologies influenced by German research. British aircraft showed similar influences. Soviet designs too bore the mark of captured German technology, though Soviet authorities were reluctant to acknowledge foreign contributions. The impact of captured Luftwaffe aircraft extended beyond immediate technical insights. They demonstrated the pace of aviation progress and the necessity of continuous innovation. American military planners, seeing what Germany had achieved in a few years, recognized that technological superiority could not be taken for granted. This realization drove increased investment in aerospace research and development. The jet age had arrived, and captured German aircraft had provided a preview of what was coming. The human stories behind these aircraft continued to unfold. Luftwaffe pilots, scattered after the war, struggled to adjust to peace. Some remained in Germany, rebuilding their lives in a shattered nation. Others emigrated, finding opportunities abroad. A few were recruited by Allied air forces, sharing their expertise with former enemies. These men had flown the aircraft the Allies now studied. Their perspectives, when they chose to share them, offered insights that documents alone could not provide. Gustav Rödel, an ace with 98 confirmed victories, spent time in Soviet captivity before returning to West Germany. He later joined the new West German Air Force when it was established in 1955, flying jets that incorporated technologies pioneered by the Luftwaffe he once served. His career represented a broader pattern: continuity between the old Luftwaffe and the new German military, mediated by the technological revolution jet aircraft represented. The legacy of captured aircraft was thus complex and multifaceted. They were trophies of victory, certainly, but also teachers whose lessons would shape aviation for generations. They were reminders of what Nazi Germany had achieved, and warnings about the consequences of militarism. They were engineering marvels and flawed designs, products of brilliance and desperation in equal measure. Most of all, they were evidence that technological progress does not respect national boundaries or political systems. Good ideas, once discovered, spread inevitably, transforming the world regardless of their origins. The testing programs that followed the initial capture and cataloguing of Luftwaffe aircraft were extraordinarily comprehensive and revealed layers of technological sophistication that even Allied intelligence had not fully anticipated. At Wright Field in Ohio, which would become the center of American efforts to understand German aviation technology, engineers and test pilots worked systematically through dozens of aircraft types. Each aircraft underwent a standardized evaluation process that began with ground inspection and culminated in extensive flight testing. The ground inspection phase was meticulous. Engineers examined every aspect of each aircraft, from structural design to systems integration to manufacturing techniques. They were particularly interested in how German engineers had solved common problems. For example, the hydraulic systems on German aircraft often used different fluids and pressures than American systems. Understanding these differences helped American engineers evaluate alternative approaches to familiar challenges. The electrical systems, fuel systems, and control systems all received similar scrutiny. Manufacturing techniques also drew intense interest. German industry had faced different constraints than American industry, leading to innovative solutions. Some German aircraft used construction methods designed to work around shortages of strategic materials. Others employed techniques that simplified production or required less skilled labor. American engineers recognized that these wartime innovations might have peacetime applications, particularly as the United States began transitioning from wartime to peacetime production. The flight testing phase revealed aircraft personalities that no amount of ground inspection could capture. Test pilots discovered that each aircraft type had unique characteristics, quirks, and behaviors that defined the flying experience. Some aircraft were docile and forgiving, easy for pilots to master. Others demanded constant attention and punished mistakes harshly. Understanding these characteristics was crucial for evaluating combat potential and informing American aircraft development. The WW2 335 File, a conventional twin-engine push-pull aircraft that had served as a fast bomber and reconnaissance platform, underwent particularly thorough testing. The aircraft's unusual engine arrangement, one engine pulling in the nose, another pushing in the tail, fascinated American engineers. This configuration provided excellent aerodynamics with minimal drag, but it also created unique engineering challenges. How did German engineers manage cooling for both engines? How did they handle asymmetric thrust if one engine failed? How did pilots manage the complex engine controls? Test flights revealed that the WW2 335 was surprisingly pleasant to fly despite its unconventional layout. The cockpit was spacious and well-appointed, visibility was excellent, and the aircraft handled smoothly at cruise speeds. However, single-engine operation was tricky, requiring careful pilot technique to maintain control. American test pilots concluded that the WW2 335 represented a successful design that had been overtaken by the advent of jet aircraft. In a world without jets, it would have been formidable. In the emerging jet age, it was already obsolete. The Junkers Ju-888, Germany's versatile medium bomber that had served in roles ranging from level bombing to night fighting to reconnaissance, also received extensive evaluation. The Ju-888 had been one of Germany's most important aircraft, produced in enormous numbers and constantly modified to meet changing operational requirements. Allied forces had encountered it throughout the war and had captured numerous examples. Now, with the war over, engineers could examine it thoroughly without the pressure of combat operations. What they found was an aircraft that exemplified German engineering philosophy. The Ju-888 was robust, adaptable, and sophisticated. Its systems were well integrated and thoughtfully designed. However, it was also complex, requiring extensive maintenance and skilled crews. German engineers had prioritized capability and performance over ease of maintenance, a design philosophy that made sense when expecting a short war, but proved problematic in a prolonged conflict where maintenance became increasingly difficult. American engineers compared the Ju-888 to American medium bombers like the B-25 Mitchell and found interesting contrasts. The American aircraft tended to be simpler, more rugged, and easier to maintain. The German aircraft was more sophisticated and in some respects more capable, but at the cost of complexity. Neither approach was inherently superior. Each reflected different priorities and constraints. American designers took note of German solutions to various technical problems, while recognizing that different design philosophies suited different industrial and operational contexts. Soviet testing programs paralleled Western efforts but followed different methodologies and served different purposes. The Soviet Union, emerging from the war with enormous military might but technological limitations in several key areas, viewed captured German aircraft as opportunities for rapid advancement. Soviet engineers were particularly interested in jet propulsion, an area where Soviet development lagged significantly behind both German and Western efforts. At facilities around Moscow, Soviet engineers dismantled captured Mi-262s bolt by bolt, documenting every detail. Soviet technical drawings of German jets were extraordinarily thorough, showing every component and assembly process. These drawings would serve as templates for Soviet jet development. The Yakovlev Yak-15, one of the Soviet Union's first jet fighters, bore obvious influences from the Mi-262 in its layout and design philosophy. though Soviet engineers adapted rather than simply copied German designs. Soviet interrogation of captured German engineers was more aggressive and comprehensive than Western approaches. Thousands of German technical personnel found themselves compelled to work for Soviet programs, some willingly, others under duress. Entire design bureaus were relocated to the Soviet Union, bringing with them not just knowledge but also equipment and documentation. The BMW and Junkers engine factories, captured by Soviet forces, were dismantled and shipped east. German workers followed, continuing production now under Soviet direction. The ethical dimensions of this compelled labor troubled some observers, particularly in the West. However, Cold War imperatives generally overrode ethical concerns. Both sides recognized that technological advantage could determine the outcome of future conflicts. If one side hesitated on ethical grounds while the other side aggressively exploited captured technology and personnel, the hesitant side would find itself at a disadvantage. This logic drove American programs like Operation Paperclip as much as it drove Soviet recruitment of German specialists. Werner Heisenberg, though primarily known for his physics work, also contributed to aeronautical research during the war. His theories about turbulence and fluid dynamics influenced German wind tunnel design and testing methodology. After the war, Heisenberg was briefly detained by American forces but was never prosecuted. He eventually returned to Germany, where he continued his scientific career. His case illustrated the complexity of dealing with German scientists and engineers. Many had participated in the Nazi war effort without being ardent Nazis themselves, complicating efforts to assign moral responsibility. The Focke-Wulf TAR-183, an advanced jet fighter project that existed only as prototypes when the war ended, became a subject of particular interest and controversy. American forces captured several incomplete airframes and extensive documentation. The TAR-183 represented Kurt Tank's vision for a second-generation jet fighter, incorporating lessons learned from the Me-262 and addressing many of its weaknesses. The aircraft featured improved engines, better armament, and enhanced performance. However, the TR-183 never flew, and analyzing an aircraft that existed only on paper and as partial prototypes presented unique challenges. American engineers studied the design carefully, evaluating its aerodynamics through wind tunnel tests of models and components. They concluded that the TR-183 would have been a formidable aircraft had it entered production. More importantly, studying the design revealed German thinking about next-generation fighters, insights that influenced American jet fighter development in the late 1940s. The Arado R-234, as the world's first operational jet bomber, underwent particularly extensive evaluation by multiple Allied powers. American, British, and French forces all secured examples and each conducted independent testing. The results were remarkably consistent. The R-234 was fast, relatively easy to fly, and demonstrated that jet bombers were practical. However, its range was limited, its bomb load was modest, and it lacked defensive armament. These limitations meant that while the aircraft proved the concept of jet bombers, it did not represent a complete solution to strategic bombing requirements. Nevertheless, the R-234 influenced bomber development profoundly. American engineers studying the aircraft recognized that jet propulsion offered bombers the same advantages it offered fighters: higher speed, better altitude capability, and improved performance. Within a few years, American jet bombers like the B-45 Tornado would enter service, followed by more advanced types like the B-47 Stratojet. These aircraft traced their conceptual lineage partly to the R-234, though American designs incorporated many improvements and addressed the limitations German designers had encountered. British evaluation of the R-234 focused particularly on its engines, the BMW 003 turbojets. British engine manufacturers were developing their own jets, but the BMW engines offered alternative approaches to various design challenges. British engineers noted the BMW engine's construction techniques, cooling methods, and combustion chamber design. Some of these features influenced subsequent British engine development, though British designers were careful to claim that their work was independent. The reality, as often happened in technology transfer, was more nuanced. Ideas flowed freely once barriers fell, and distinguishing genuine independent development from influenced development was often impossible. French testing of captured aircraft served somewhat different purposes than American or British programs. France, devastated by war and occupation, lacked the resources for extensive research programs. However, France had a proud aviation tradition and was determined to rebuild its aircraft industry. Captured German aircraft provided templates and inspiration. French engineers studied them carefully, learning what worked and what did not. Several French post-war aircraft showed clear German influences, particularly in aerodynamic design and systems integration. The question of proper attribution for technological advances became increasingly political as the Cold War intensified. Who had really invented the swept wing? German researchers had documented its benefits extensively and applied swept wings to operational aircraft. However, American and British researchers could point to earlier theoretical work that had explored similar concepts. The Germans had been first to apply swept wings to jets, but the underlying aerodynamic principles had been understood earlier, at least in theory. Similar debates arose about other technologies. Who deserved credit for practical jet propulsion? The British had the Gloucester Meteor, which entered service before the Me-262. However, German jets were in some respects more advanced. The Germans had pioneered axial flow turbojets, while early British jets used centrifugal designs. Each approach had advantages and disadvantages, and both would find applications in subsequent decades. These debates mattered because they shaped national narratives about technological achievement and military capability. Nations took pride in their technological accomplishments, and attributing key developments to captured German technology rather than domestic innovation could be politically uncomfortable. American officials generally emphasized that American aircraft incorporated lessons learned from German designs rather than copying them. This phrasing suggested that American engineers had taken German ideas and improved upon them rather than simply implementing German concepts wholesale. The distinction had some validity. American aircraft that showed German influence, like the swept-wing F-86 Sabre, were not simple copies of German designs. They incorporated American engineering philosophy, American manufacturing techniques, and American operational requirements. The swept wing came from German research, but the overall aircraft was distinctly American. Similar patterns appeared in British and Soviet designs: influence without simple copying, adaptation rather than imitation. The moral dimensions of using technology developed by Nazi Germany continued to trouble some individuals, even as the technology was implemented widely. The German aviation industry had employed slave labor extensively. Concentration camp prisoners worked in aircraft factories, often in horrific conditions. Many died from mistreatment, starvation, disease, or accidents. Underground factories carved into mountains used forced labor to escape Allied bombing. When Allied engineers examined German aircraft and factories, they found evidence of this brutality everywhere. Some questioned whether using technology tainted by such suffering was morally appropriate. Should the Allies benefit from research and development that had been accomplished partly through slave labor? Should aircraft built by prisoners be studied and emulated? The questions were uncomfortable, and the answers far from clear. The pragmatic response was that the aircraft existed, the knowledge existed, and refusing to use it would not undo past suffering. Moreover, the emerging Cold War made technological advantage imperative. American and Soviet leaders both prioritized military capability over moral qualms about technology's origins. Yet the moral questions did not disappear. They resurfaced periodically, particularly as documentation of slave labor in German industry became more widely known. Museum exhibits displaying German aircraft began including information about how they were produced, contextualizing impressive engineering within the brutal reality of Nazi Germany's war economy. This contextualization helped visitors understand that technological achievement did not excuse or erase evil, and that studying history required grappling with uncomfortable truths. The distribution of captured aircraft among the Allied powers also revealed tensions and power dynamics within the alliance. Britain, economically devastated by 6 years of war, lacked resources to conduct testing programs on the scale America pursued. British requests for access to certain aircraft were sometimes denied or delayed by American authorities who prioritized their own programs. British officials resented this treatment, feeling their wartime contributions and sacrifices deserved better consideration. American officials focused on their own priorities and operating from a position of overwhelming economic and military strength, were less sympathetic to British concerns. They recognized Britain's contributions but saw no reason to subordinate American interests to British needs. This dynamic created friction that, while minor compared to the growing East-West tensions, showed that even close allies competed for advantage and sometimes pursued divergent interests. French officials faced similar frustrations. France had been liberated but occupied for 4 years. Its aviation industry was shattered. Its technical expertise was depleted, yet France sought to rebuild as a major power, which required access to advanced technology. The French claimed significant numbers of captured aircraft, but these claims were not always honoured by American and British forces who controlled most German territory. French frustration with Anglo-American domination of captured technology was one factor among many that contributed to France's later pursuit of independent military capabilities, including development of indigenous nuclear weapons and advanced aircraft. Not all captured German aircraft met straightforward fates. Some disappeared into classified programs, their existence acknowledged only decades later. Others sparked international incidents that threatened the fragile post-war peace. Still others became pawns in the emerging Cold War, their technology coveted by both sides of the new global divide. The story of these aircraft reveals as much about post-war politics as it does about aviation technology. In the spring of 1946, a curious incident occurred at Farnborough. A Soviet delegation arrived ostensibly to examine British test procedures. Their actual interest was the captured German aircraft housed there. British officials, wary of Soviet intentions, allowed only limited access. The Soviets, frustrated by restrictions, lodged formal complaints. The tension reflected a larger truth. The wartime alliance was fracturing, and technology had become a weapon in the emerging Cold War. Each captured aircraft represented potential military advantage, and no power wished to share more than necessary. The division of captured aircraft had been negotiated through the Tripartite Naval Commission, but aviation technology fell under different arrangements. In theory, the United States, Britain, and the Soviet Union would share information about German aircraft. In practice, each power held back what it considered most valuable. The Americans had captured the majority of advanced jets. The Soviets controlled factories and many engineers. The British had secured key research facilities. Each side understood that cooperation was limited, and the race to exploit German technology was on. One of the most controversial cases involved the Junkers Ju-388, Germany's first jet-powered heavy bomber project. Only incomplete prototypes existed at war's end, but documentation was extensive. American forces captured the primary prototype and most documents. Soviet forces, however, claimed to have found a second prototype and associated plans. Whether this Soviet claim was true or whether they had simply obtained copies of American captured documents remained unclear. The disagreement highlighted how captured technology could become a source of international friction. The fate of German scientists and engineers added another layer of complexity. While Operation Paperclip brought many to the United States, the Soviet Union conducted its own recruitment program with different methods. Entire design bureaus were sometimes relocated to the Soviet Union, personnel and equipment together. German engineers found themselves continuing their work under Soviet direction, unable to refuse. Some adapted to their circumstances. Others waited for opportunities to escape. The moral dimensions of this compelled service troubled some Western observers, but Cold War priorities generally outweighed ethical concerns. Kurt Tank, designer of the Focke-Wulf FW1, 90 series took a different path. Rather than work for the Allies or Soviets, he fled to Argentina in 1947. There, he continued aircraft design work, creating several types for the Argentine Air Force. His most notable design, the IA-33 Pulkitz, bore clear resemblance to late-war German jet projects. Tank's story illustrated how German aviation expertise spread globally, not just to the major powers, but to any nation willing to offer employment and resources. The discovery of underground aircraft factories presented Allied forces with unexpected challenges. At Kala, Soviet forces found a massive underground facility designed for Me-2-62 production. Tunnels stretched for miles, carved into solid rock. The Soviets dismantled usable equipment and shipped it to the USSR. The Americans, upon learning of the facility's sophistication, realized how close Germany had come to achieving truly protected production capability. Had the war continued, such facilities might have sustained aircraft production despite Allied bombing. The revelation influenced post-war thinking about strategic bombing and industrial protection. The Backenbach 349 Natter program revealed the depths of German desperation. This vertical launch rocket interceptor represented a radical solution to Allied bomber streams. Pilots would launch from vertical rails, rocket to altitude, fire unguided rockets at bomber formations, then eject and parachute down. The aircraft itself would crash. 36 production Natters were completed, but only one was ever flown with a pilot aboard. That flight on March 1, 1945, ended in tragedy when test pilot Lothar Sieber was killed. The program was abandoned before operational deployment. Allied investigators who examined surviving Natters were horrified by the concept. The aircraft was essentially expendable, and pilots barely more so. The cockpit offered minimal protection. Control systems were crude. Success required not just courage, but recklessness. American test pilots, when asked if they would fly such an aircraft, uniformly declined. The Natter stood as evidence of what desperation could produce. Innovative solutions to technical problems combined with disregard for human life. Yet some elements of the Natter program proved valuable. Its vertical launch system and rocket motor offered insights into missile technology. American researchers studying the Natter saw applications beyond manned aircraft. The concept of vertically launched interceptors, though abandoned for piloted aircraft, would resurface in surface-to-air missile programs. Thus, even the Natter, perhaps the most desperate of German aircraft projects, contributed to future developments. The WW2 335 Pfeil, a conventional twin-engine aircraft with an unusual push-pull engine arrangement, told a different story. Several examples survived the war in flying condition. The type had served effectively as a fast bomber and reconnaissance aircraft, using its speed to avoid interception. American and French forces both captured Do-335s extensively. Test pilots praised its performance but noted that it was ultimately outclassed by jets. Nevertheless, the French were sufficiently impressed to consider licensed production for their own air force. The plan was abandoned only because jet aircraft had rendered such designs obsolete. The question of what to do with captured German designs became politically sensitive. If the United States openly copied German aircraft, it might suggest American inferiority. If designs influenced by German technology were fielded without acknowledgement, it could be seen as intellectual theft. The solution was careful management of public statements. American aircraft were described as incorporating lessons learned from German designs rather than copying them directly. The distinction was subtle but important for national pride. British approaches were similar. The de Havilland Vampire jet fighter, which entered service in 1946, shared certain characteristics with German jets, but was described as independently developed. This was technically true. Design had begun before extensive access to German technology. However, captured German research certainly influenced refinements and subsequent British designs. The line between independent development and technology transfer was often blurry. The Soviet Union showed less concern about such perceptions. Soviet aircraft designed in the late 1940s clearly incorporated German technology, and Soviet authorities made little effort to hide this fact domestically. The Mikoyan-Gurevich MiG-15, which would achieve fame in the Korean War, owed obvious debts to German swept-wing research and captured engine technology. Our Soviet engineers saw no shame in building on German foundations. They viewed it as pragmatic exploitation of available resources. One of the most intriguing discoveries came from the archives of the Horten brothers. Reimar and Walter Horten had been developing flying wing aircraft since the 1930s, pursuing their vision of maximally efficient aircraft. Their designs progressed from gliders to powered aircraft to jets. The Ho-229 represented the culmination of their work, but documents revealed more ambitious plans. A massive flying wing jet bomber with transatlantic range designated the Ho-68. This aircraft could have threatened the United States directly had it been completed. The Ho-68 existed only as drawings and a scale model, but Allied analysts took the concept seriously. A jet bomber capable of reaching American cities represented a strategic threat unlike any previous aircraft. The discovery drove American interest in continental air defense and accelerated programs to develop jet interceptors. Captured German designs, even those never built, influenced strategic planning by showing what future threats might look like. In 1947, an unexpected controversy erupted when American news media published photographs of captured German aircraft. The images showed Mi-262s and other jets being tested at Wright Field. Soviet officials protested, claiming the photographs violated agreements about shared technology. American officials responded that testing captured equipment was a sovereign right. The dispute highlighted how captured aircraft had become sensitive political assets. Every nation wanted the technology, but feared others gaining advantage from it. The fate of prototype aircraft was particularly contentious. These one-of-a-kind machines represented the cutting edge of German development. The Focke-Wulf TAR-183, an advanced jet fighter project, existed only as prototypes when Germany surrendered. American forces captured several incomplete airframes. Soviet forces claimed they had found additional examples. Whether both claims were true or whether someone was bluffing remained uncertain. Prototype aircraft lacking production documentation were harder to verify, which created opportunities for exaggeration and deception. Some aircraft were lost to simple neglect. With thousands of German planes scattered across Europe, careful accounting was impossible. Aircraft left at remote airfields sometimes deteriorated before anyone could secure them. Others were damaged by locals salvaging materials. The chaos of post-war Europe claimed many aircraft that might otherwise have been preserved. By the time authorities recognized the historical value of certain types, examples had disappeared. The Heinkel Heim-177, a strategic bomber that had been used extensively on the Eastern Front, largely vanished after the war. Though hundreds had been built, few complete examples survived. Most had been destroyed in combat or scrapped afterward. The Soviet Union captured several but did not preserve them. By the 1950s, when interest in preserving historical aircraft grew, finding an intact He-177 proved nearly impossible. The type had simply been too common to seem worth saving at the time. The Blohm & Voss BV-141, an asymmetric reconnaissance aircraft with a unique design, fared only slightly better. This unusual aircraft featured an asymmetric crew gondola offset to the left of its centerline. Only a few were built, and most were destroyed by retreating German forces. One complete example was captured by Americans and shipped to Wright Field. After evaluation, it was stored. Decades later, it emerged from storage to become a museum piece, one of the few surviving examples of this peculiar design. Captured German research aircraft revealed how far Nazi Germany had progressed towards supersonic flight. The DFS-346, a rocket-powered research aircraft designed to investigate high-speed flight, had been under development when the war ended. Incomplete examples were found by both American and Soviet forces. The DFS-346 was intended to reach speeds exceeding the speed of sound, though whether it could have done so remains debatable. Its design influenced both American and Soviet supersonic research programs. The question of credit for technological advances became increasingly political. Who invented the swept wing? German researchers had extensively documented its benefits, but Americans could point to earlier theoretical work by American scientists. Who developed practical jet fighters first? The British had the Gloucester Meteor, which entered service before the Mi-262, but German jets were more advanced in some respects. These debates mattered because they shaped narratives about national technological prowess. In truth, aviation progress was cumulative and international. German advances built on earlier research from multiple nations. Allied advances during and after the war similarly drew on diverse sources. The capture of German aircraft accelerated certain developments but did not create them from nothing. American and British engineers had been working on jet propulsion independently. Soviet designers had their own programs. German technology provided shortcuts and validation, but not the fundamental concepts. The moral dimension of using technology developed by Nazi Germany troubled some individuals. The German aviation industry had employed slave labor. Aircraft factories used concentration camp prisoners who worked in horrific conditions. Many died from mistreatment, starvation, or accidents. When Allied engineers examined German aircraft and factories, they found evidence of this brutality. Some questioned whether using technology tainted by such suffering was appropriate. The counter-argument was pragmatic. The aircraft existed, the knowledge existed, and refusing to use it would not undo past horrors. Moreover, the emerging Cold War made technological advantage imperative. American and Soviet leaders both prioritized military capability over moral qualms about technology's origins. Engineers and pilots followed orders, studying and testing German aircraft without dwelling on how they had been produced. This tension between utility and ethics played out in discussions about employing German engineers. Some argued that bringing Nazi collaborators to America or Britain rewarded complicity in evil. Others contended that many engineers had been apolitical technicians who simply did their jobs. The truth varied by individual. Some German engineers had been enthusiastic Nazis, others had opposed the regime privately while professionally competent. Distinguishing between these cases was difficult, and Cold War expediency often trumped careful investigation. The distribution of captured aircraft also revealed power dynamics within the Western alliance. Britain, economically devastated by the war, lacked resources to conduct testing programs on the scale America pursued. British requests for access to certain aircraft were sometimes denied or delayed. British officials resented this treatment, feeling their wartime contributions deserved better consideration. American officials, focused on their own priorities, were less sympathetic. These frictions, though minor compared to East-West tensions, showed how even allies competed for technological advantage. The ultimate irony was that many captured German aircraft revealed problems as much as possibilities. The Me-262, for all its speed, was unreliable and difficult to maintain. The Ho-162, though cheap to produce, was a compromised design with limited capabilities. Even the advanced jets that impressed Allied engineers were often flawed in practical terms. Germany had achieved remarkable innovations, but these came at enormous cost and often sacrificed operational practicality. This realization shaped post-war aircraft development. Allied designers sought to combine German innovations with more robust engineering and better reliability. The goal was not just high performance, but sustained operational capability. American and British jets entering service in the late 1940s reflected this philosophy. They incorporated German-inspired features like swept wings, but emphasized reliability, maintainability, and ease of production. The result was aircraft that were less cutting-edge than late-war German jets, but far more practical. By 1949, the initial phase of exploiting captured German aviation technology was complete. The most valuable aircraft had been tested. Key engineers had been recruited or their knowledge extracted. Design insights had been integrated into Allied programs. What remained were the aircraft themselves, now mostly in storage or museums, and the questions they raised about innovation, ethics, and the nature of technological progress. These questions would continue to resonate as the jet age accelerated and new generations of aircraft pushed performance boundaries that German designers had only imagined. The human dimension of this story continued to unfold in profound and sometimes unexpected ways. Thousands of Luftwaffe personnel, from pilots to mechanics to engineers, faced uncertain futures in the aftermath of Germany's collapse. Many were held in prisoner-of-war camps scattered across Europe, awaiting repatriation that could take months or even years. Others were recruited by Allied powers to continue their work, now serving former enemies. The choices they made and the paths they followed reveal much about human adaptability and the complex moral landscape of the post-war era. Willy Messerschmitt himself, the designer of many famous Luftwaffe aircraft including the Bf 109 and the Me-262, was detained by American forces in May 1945. He spent 2 years in custody, during which he was extensively interrogated about his aircraft designs and his relationship with the Nazi regime. Messerschmitt defended his work as that of a designer and engineer rather than a political figure. He claimed he had focused on technical problems rather than the political implications of his work. American officials were uncertain what to do with him. Messerschmitt's expertise was undeniable and valuable. His understanding of high-speed aerodynamics and jet propulsion was among the best in the world. Yet his association with the Nazi regime and his use of slave labor in aircraft production were equally undeniable. American authorities eventually released Messerschmitt in 1947, but prohibited him from aircraft design work for several years. He would later return to aviation, playing a role in rebuilding German industry during the 1950s and 60s. His post-war career remained controversial, with some viewing him as a rehabilitated engineer and others seeing him as someone who had never fully accounted for his complicity in Nazi crimes. Ernst Heinkel, another prominent German aircraft designer whose company produced the He-111 bomber and the He-178, the world's first jet aircraft, faced similar questions. Heinkel had been an early adopter of jet propulsion technology, and his company's research had been instrumental in Germany's jet development. Like Messerschmitt, Heinkel claimed he was primarily interested in technical achievement rather than politics. Also, like Messerschmitt, he was prohibited from aircraft work for several years before eventually returning to the aviation industry. Kurt Tank, designer of the Focke-Wulf FW190 series, took a different path entirely. Rather than work for the Allies or Soviets or wait for permission to resume work in Germany, Tank fled to Argentina in 1947 with the assistance of Argentina's government, which was actively recruiting German technical experts. There, Tank continued aircraft design work, creating several types for the Argentine Air Force. His most notable design was the IA-33 Pulky II, a jet fighter that bore clear resemblance to late-war German projects. The aircraft showed that German design philosophy had spread globally, not just to the major powers, but to any nation willing to offer employment and resources to German engineers. The Allied technical intelligence operations also uncovered Germany's extensive network of wind tunnel facilities, which proved to be among the most valuable captures of the entire program. At Kogel AMC near Munich, the Allies found one of the world's most advanced supersonic wind tunnels. This facility, designed to test aircraft and components at speeds exceeding the speed of sound, had enabled German engineers to explore aerodynamic phenomena that Allied researchers were only beginning to understand. The tunnel could generate airflows at Mach 1.4, allowing researchers to study shock waves, compression effects, and other high-speed aerodynamic phenomena. After the war, this facility became a point of contention among the Allies. The United States wanted it intact for transfer to America. France claimed it should remain in the occupation zone it controlled. The Soviet Union demanded access to its technical specifications. The dispute was eventually resolved by partially dismantling the facility and dividing its equipment between the victorious powers. The United States received substantial portions, which were shipped across the Atlantic and reassembled at facilities including the NACE Langley Research Center and Wright Field. These captured wind tunnels would serve American aerospace research for decades, contributing to developments ranging from supersonic fighters to space vehicles. Additional wind tunnel facilities were discovered at Göttingen, where the Kaiser Wilhelm Institute for Fluid Dynamics had conducted cutting-edge research since the 1920s. The Göttingen facilities were less dramatic than Kochel, but equally valuable. They contained decades of experimental data and had been home to some of Germany's most brilliant aerodynamicists. Allied teams seized the documentation and equipment, then recruited key personnel to continue their work for Allied programs. By September 1945, the initial phase of aircraft collection, evaluation and technology transfer was largely complete. Hundreds of German aircraft had been shipped to Allied nations for testing. Thousands more had been destroyed in place. The most valuable technical personnel had been identified and recruited or detained. Yet questions remained. What would happen to the aircraft that had been preserved? How would captured technology influence future aviation development over the long term? And what about the aircraft still hidden or undiscovered? In the chaos of Germany's collapse, numerous aircraft had been concealed or abandoned in remote locations, and over the following years and even decades, more would be found. In 1952, Austrian hikers discovered a nearly intact Bf-109 in a remote alpine valley. The aircraft had apparently been flown there by its pilot in the war's final days, then abandoned. The dry alpine climate had preserved it remarkably well. Local authorities notified aviation historians, and the aircraft was eventually recovered and restored. Today, it resides in a museum, one of the best preserved examples of its type. Similar discoveries occurred sporadically throughout the Cold War years and beyond. In the 1970s, researchers found several aircraft deliberately sunk in lakes by retreating German forces. In the 1980s and 90s, construction projects occasionally uncovered buried aircraft components. As recently as the 21st century, aircraft hunters using modern technology, like ground-penetrating radar and metal detectors, have located crash sites and hidden caches of aircraft parts. Each discovery adds to our understanding of what happened in those chaotic final weeks of the war. The story of the Luftwaffe's end was not just about machines and technology, it was fundamentally about people, decisions, and consequences that echoed through generations. Each captured aircraft represented years of design work, testing, and production involving thousands of individuals. Each had been flown by pilots who believed in their mission or simply followed orders in a totalitarian state. Each now served as a trophy, a teaching tool, or a warning about the costs of war and totalitarianism. As the Allies began to fully understand what they had captured, the profound impact of German aviation technology on the future of flight started to become clear. The next decades would reveal just how thoroughly these aircraft and the knowledge they contained would reshape aviation. German research would influence everything from commercial airliners to military jets to space vehicles. The swept wing, pioneered by German researchers, would become ubiquitous. Jet propulsion, proven practical by German engineers, would replace piston engines in nearly all high-performance aircraft. The lessons learned from captured Luftwaffe planes would ripple through aviation history for generations. Museums around the world today display Luftwaffe aircraft as centerpieces of their World War II collections, each one a tangible connection to a pivotal moment in history: the Messerschmitt. Me-262 at the Smithsonian National Air and Space Museum in Washington draws countless visitors who marvel at its sleek lines and historical significance. The carefully restored Arado R-234 at the Stephen F. Udvar-Hausy Center impresses viewers with evidence of German engineering sophistication. Similar aircraft at museums in Britain, Germany, Russia, France, and elsewhere serve as educational tools and historical monuments. Yet for every aircraft preserved in a museum, hundreds or thousands were lost to destruction, neglect, or the simple passage of time. The winnowing was inevitable, given the numbers involved and the chaotic conditions of post-war Europe. Some aircraft types that were relatively common in 1945 became rare by the 1950s and are now represented by only single surviving examples. Others have disappeared entirely from the physical record, existing now only in photographs, drawings, and the memories recorded by those who saw them. The technological legacy of the captured Luftwaffe continues to influence aviation even in the 21st century. Modern fighter aircraft still employ swept wings and jet propulsion, technologies that German engineers pioneered or significantly advanced. Commercial airliners use aerodynamic principles first explored in German wind tunnels. Even spacecraft benefit from German research into high-speed aerodynamics and rocket propulsion. The chain of influence is long and often indirect, but connections exist between the Me-262, captured in Bavaria in 1945, and the most advanced aircraft flying today. The question of aircraft preservation became increasingly important as the 1950s and 60s progressed, and people began to recognize that many historically significant aircraft had already been lost. Aviation museums and enthusiasts launched efforts to locate, document, and preserve remaining examples of Luftwaffe aircraft. These efforts sometimes led to dramatic discoveries and rescues of aircraft that had been forgotten or abandoned decades earlier. In 1963, a team of researchers discovered a Me-262 buried beneath a concrete runway at an abandoned German airfield. The aircraft had apparently been hidden by retreating German forces, then paved over during post-war reconstruction. Using records and interviews with local residents, the team pinpointed the location and began excavation. The work was difficult and expensive, requiring removal of substantial amounts of concrete and soil. However, when they finally uncovered the aircraft, they found it remarkably well preserved. The dry conditions beneath the concrete had protected it from moisture and corrosion. After careful extraction, the Me-262 was transported to a restoration facility. Years of painstaking work followed, with craftsmen replacing corroded parts, restoring damaged structures, and bringing the aircraft back to display condition. Today, this aircraft serves as an example of what can be achieved through determined preservation efforts. It stands in a museum as testament both to German engineering and the dedication of those who saved it from oblivion. Similar stories repeated across Europe and even beyond. In Sweden, a Me-163 Comet was discovered in storage at a military facility, where it had been kept since 1946. Swedish forces had obtained it from British authorities shortly after the war, intending to study it, but interest had waned and the aircraft was forgotten. When rediscovered in the 1970s, it was found to be in excellent condition, having been stored indoors and protected from the elements. Swedish authorities agreed to loan it to a museum, where it became one of only a handful of surviving comets available for public viewing. The story of the Horten Ho 229 flying wing that was captured at Friedrichsroda and shipped to the United States in 1945 had an interesting epilogue. For decades, the aircraft remained in storage at what became the National Air and Space Museum's Paul E. Garber facility in Maryland. It was too fragile and valuable to display without extensive restoration. In the 2000s, the museum finally undertook a complete restoration project. The work revealed fascinating details about the aircraft's construction and confirmed that it had been closer to completion than initially thought. When the restoration was finished, the Ho 229 went on display, where it continues to astound visitors with its radical design. Aviation archaeology, the practice of locating and excavating crash sites and hidden aircraft, emerged as a distinct field in the later 20th century. Enthusiasts using metal detectors, archival research, and interviews with witnesses located numerous crash sites across Europe. Some contained wreckage that was purely historical interest. Others yielded components that could be used in restoration projects. Occasionally, the archaeology uncovered complete aircraft that had been missed in earlier recovery efforts. In 1998, a team located an intact WW190A in a Russian forest. The aircraft had been abandoned by retreating German forces and had sat undisturbed for more than 50 years. The forest had grown up around it, and trees now grew through parts of the structure. Nevertheless, much of the aircraft remained intact. After lengthy negotiations with Russian authorities, the team received permission to recover it. The aircraft was carefully extracted from the forest and transported to Germany, where it underwent restoration. The process took years, but the result was an exceptionally authentic example of a FW190A that had seen actual combat service. These rediscoveries and restorations enriched the historical record and provided tangible connections to the past. Each preserved aircraft told stories that documents alone could not convey. The wear patterns on controls, the patches on damaged areas, the markings and modifications all provided evidence of how these aircraft had been used and maintained. Museums that displayed carefully restored aircraft could offer visitors an experience approaching what it was like to see these machines when they were operational. The 1950s marked a transition in how captured Luftwaffe aircraft were viewed. No longer urgent intelligence prizes, they became historical artifacts. Museums began acquiring examples for preservation and display. The Smithsonian Institution in Washington received several important aircraft, including an Me-262 and an R-234. The Royal Air Force Museum at Hendon acquired British-tested examples. These preserved aircraft would educate future generations about World War II aviation and the technological revolution jets represented. The preservation process was not systematic. Many aircraft types were represented by single surviving examples, if any. Common types like the Bf-109 fared better, with dozens preserved worldwide. Rare types often disappeared entirely. The Henschel H-129, Germany's first jet-powered attack aircraft, existed in only 2 or 3 complete examples by the 1960s. Efforts to find and preserve additional aircraft came too late for many types. What survived was often a matter of chance rather than deliberate choice. Wright Field's collection became the foundation for the National Museum of the United States Air Force. After testing concluded, most aircraft were placed in storage. Some were displayed as curiosities, others remained in warehouses, forgotten for decades. Periodic inventories occasionally revealed unexpected treasures, prototype components, rare engines, or aircraft thought lost. The museum gradually organized its collection, restoring aircraft and placing them on permanent display. Today, the museum's German aviation exhibit includes multiple jets and experimental aircraft. The influence of captured German aircraft on Cold War aviation was profound and lasting. The swept-wing revolution that transformed fighter design in the late 1940s traced directly to German research. American aircraft like the F-86 Sabre and the F-100 Super Sabre incorporated swept wings for transonic performance. Soviet designs, including the MiG-15 and MiG-17, did likewise. British aircraft such as the Hawker Hunter followed similar principles. Within a decade of Germany's defeat, swept wings had become standard for high-performance jets. German research into supersonic flight also bore fruit in Allied programs. Wind tunnel data captured from German facilities provided Americans with years of research at no cost. American experimental aircraft of the 1950s, including the Bell X-1, which broke the sound barrier in 1947, benefited from this knowledge. German aerodynamicists who came to America through Operation Paperclip contributed directly to these programs. Their expertise complemented American efforts and accelerated progress. The Korean War, which erupted in June 1950, provided the first major combat test of jets, influenced by German technology. American F-86 Sabres faced Soviet MiG-15s over the Yalu River. Both aircraft incorporated features derived from captured German designs. The irony was profound. Former enemies now flew aircraft descended from German innovations, fighting each other in a conflict neither had anticipated. Pilots on both sides flew swept-wing jets that would not have existed or would have developed much later without German research. The F-86's swept wing gave it critical advantages in high-speed maneuvering. MiG-15 pilots, flying an aircraft powered by a Soviet copy of a British jet engine but featuring German-inspired swept wings, found themselves in aircraft superior to straight-wing opponents but roughly equal to the F-86. The battles over Korea demonstrated that the German technological legacy had spread evenly to both sides of the Cold War divide. German influence extended beyond fighters. American bomber development in the 1950s produced aircraft like the Boeing B-47 Stratojet, featuring swept wings and other design elements traced to German research. The B-52, which would become America's premier strategic bomber, also incorporated swept wings. These aircraft dominated American nuclear deterrence for decades, their designs rooted partly in technology captured from Nazi Germany. The connection between German wartime research and American Cold War military power was direct and undeniable. Soviet bomber development showed similar patterns. The Tupolev Tu-16, a swept-wing jet bomber that entered service in 1954, clearly reflected German influence. Tupolev designers had access to captured German documentation and employed German engineers during development. The result was an aircraft comparable to American types, enabling the Soviet Union to field a credible strategic bombing capability. Again, captured German technology had leveled the playing field between superpowers. The Vietnamese War provided another chapter in this story. American aircraft flying over Vietnam in the 1960s and 70s were descended from designs influenced by German research. The F-4 Phantom, F-105 Thunderchief, and other types fighting over Southeast Asia incorporated aerodynamic principles and design features that trace back, in part, to captured Luftwaffe technology. The chain of influence was long and complex, but connections existed. Meanwhile, the aircraft themselves, those physical examples captured in 1945, continued their journeys. Some remained in museums, carefully maintained and occasionally restored. Others deteriorated in storage, their fate uncertain. A few were rediscovered and rescued from obscurity. The process of locating, identifying and preserving historic aircraft became an ongoing mission for aviation enthusiasts and historians. In 1978, an American team discovered an Mi-262 buried beneath a runway in Germany. The aircraft had been hidden by retreating German forces, then forgotten. Excavation and restoration took years, but the aircraft eventually joined museum collections. Similar discoveries occurred periodically. Aircraft hidden in barns, buried in fields, or lost in swamps. Each find added to the historical record and reminded people of the chaos that had followed Germany's collapse. The United States continued testing captured German aircraft well into the 1950s for specialized purposes. Some were used in comparative evaluations against new American jets. Others served in research programs exploring specific aerodynamic questions. The last operational flight of a captured Mi-262 occurred in 1956, more than a decade after capture. After that, surviving examples were retired to museums or storage, their testing value exhausted. Britain followed a similar timeline. The RAF Museum preserved several captured aircraft, while others were scrapped after testing concluded. Eric Brown, who had flown so many captured German aircraft in the immediate post-war years, later wrote extensively about his experiences. His books and articles provided detailed accounts of what those aircraft were like to fly, offering insights that technical documents alone could not convey. Brown's perspective was unique. He had flown virtually every significant German aircraft type, often shortly after capture while the aircraft was still in wartime configuration. The Soviet Union remained more secretive about its captured aircraft and testing programs. Information about Soviet evaluation of German jets emerged slowly, often years or decades after the fact. Soviet test pilots' memoirs, published after the Cold War ended, revealed extensive testing programs that paralleled Western efforts. Soviet engineers had been no less thorough in studying German technology, though their methods and priorities sometimes differed from American approaches. By the 1980s, captured German aircraft had become valuable historical artifacts rather than sources of current technology. Aviation had progressed far beyond what German designers had achieved. Supersonic fighters, strategic bombers capable of intercontinental flight, and eventually stealth aircraft represented capabilities German engineers could only have imagined. Yet the lineage remained traceable. Modern aircraft were descendants, however distant, of the jets Germany had pioneered. The question of proper historical credit became less contentious with time. Serious historians acknowledge German contributions to jet aviation, while recognizing that technological progress is always collective and international. German designers had built on earlier work by others. Allied designers had done likewise. The capture of German aircraft had accelerated certain developments, but had not created the jet age from nothing. Both perspectives were true. The moral questions about using technology developed by Nazi Germany never fully disappeared. Museum displays of German aircraft sometimes included information about slave labor used in their production. Educational materials acknowledged the human cost of German technological achievements. This contextualization helped visitors understand that impressive engineering did not excuse or erase the evil regime that created it. The aircraft were historical evidence, worthy of preservation and study, but not celebration. Some Luftwaffe veterans remained bitter about how their aircraft had been treated. They felt that Allied testing had sometimes been dismissive, or that captured aircraft were not properly maintained before testing. From their perspective, their machines had not received fair evaluation. Allied test pilots, however, countered that they had approached captured aircraft objectively and reported both strengths and weaknesses honestly. The difference in perspective reflected deeper wounds. Veterans of any defeated military often struggle with how history remembers their service. The international community of aviation historians and enthusiasts gradually developed consensus about preserving remaining Luftwaffe aircraft. Organizations dedicated to aviation history worked to locate, document, and when possible, restore surviving aircraft. The work was expensive and time-consuming, but resulted in multiple aircraft being saved from deterioration. Today, examples of most significant Luftwaffe types exist in museums worldwide, ensuring future generations can see these machines. Restoration efforts sometimes revealed surprises. When museums disassembled aircraft for restoration, they occasionally found modifications, battle damage, or construction details not documented elsewhere. Each aircraft became a physical archive containing information that paper records had lost or never captured. Careful examination of surviving aircraft thus contributed to historical knowledge long after the testing programs had concluded. The story of one particular Me-262 illustrates this point. This aircraft, captured intact in 1945, underwent extensive testing before being placed in storage. Decades later, when museum staff prepared it for display, they discovered original German documents hidden in the fuselage. These documents, apparently concealed by the last German pilot to fly it, provided insights into the aircraft's service history and the pilot's final missions. Such discoveries reminded historians that each aircraft had individual stories beyond their technical specifications. The question of what would have happened if Germany had developed jet aircraft earlier fascinated both historians and the public. If the Me-262 had entered service in 1943 instead of 1944, could it have changed the war's outcome? Most historians concluded that while earlier jets would have complicated Allied operations, they could not have prevented Germany's defeat. The material and numerical advantages the Allies possessed were too great, and Germany's resource. Shortages would have limited jet production regardless of timing. Nevertheless, the question remained intriguing. Captured German aircraft had shown what was possible with jet propulsion. They demonstrated that existing technology could achieve performance levels beyond what propeller aircraft could match. This knowledge shaped strategic thinking. Military planners in the Cold War understood that technological surprise was possible, and that complacency about technological superiority could prove fatal. The German jets had arrived too late to save Nazi Germany, but their existence warned future military leaders not to underestimate potential adversaries. The captured Luftwaffe aircraft also influenced commercial aviation, though less directly. The swept-wing designs that proved so successful in military jets eventually influenced commercial airliner development. The Boeing 707, America's first successful jet airliner, featured swept wings. So did virtually every subsequent jet transport aircraft. While these designs emerged from military research, the military research had been informed by captured German technology. The connection was indirect but real. Today, aviation museums around the world display Luftwaffe aircraft as centerpieces of their World War II collections. The Me-262 at the Smithsonian, meticulously restored to its original configuration, draws countless visitors. The R-234 at the National Air and Space Museum, Stephen F. Udvar-Hazy Center, impresses viewers with its sleek design. Dozens of other aircraft, from common types like the Bf-109 to rarities like the Ho-229, serve as tangible connections to history. These preserved aircraft represent only a tiny fraction of what once existed. For every aircraft in a museum, hundreds or thousands were destroyed. The winnowing was inevitable and perhaps necessary. But it means that some types exist now only in photographs and documents. Future generations will never see certain German aircraft except as images, their forms and presence lost to time. The people who flew, designed and maintained these aircraft are nearly all gone now. The last Luftwaffe pilots who flew Me-262s in combat have passed away. The engineers who designed them have long since died. The Allied test pilots who evaluated captured aircraft have likewise departed. Their first-hand knowledge exists now only in written accounts and recorded interviews, preserved for posterity, but lacking the immediacy of living memory. Yet the aircraft themselves remain silent witnesses to a tumultuous era. They stand in museums as reminders of what happened when aviation technology leapt forward under the pressure of total war. They testify to human ingenuity and human folly in equal measure. They are engineering achievements built in service of one of history's most evil regimes. They are machines that killed Allied airmen and also machines that influenced the aircraft, that secured peace in the Cold War. They are all these things simultaneously, complex and contradictory. The ultimate legacy of captured Luftwaffe aircraft is thus multifaceted. They accelerated the jet age, bringing innovations to fruition years faster than would otherwise have occurred. They influenced aircraft design on both sides of the Cold War, shaping decades of military aviation development. They became historical artifacts that educate people about World War II and technological progress. They remind us that innovation can emerge from the darkest circumstances, and that technology itself is morally neutral, its value or harm determined by human choices. The men who designed these aircraft were complicit in Nazi Germany's crimes, whether actively or through their silence. The aircraft themselves, however, were simply machines, products of human knowledge applied to specific engineering problems. This distinction matters for how we understand both history and technology. We can study the aircraft without endorsing the regime that created them. We can learn from their design without ignoring the suffering that accompanied their production. In the end, the story of what happened to Luftwaffe aircraft after World War II is a story about knowledge transfer, technological evolution, and the complicated legacies of war. These aircraft, scattered across the world in 1945, ended up teaching the victors, serving new masters, or resting in museums. They influenced aviation development profoundly, their impact visible in nearly every jet aircraft designed in the following decades. They became bridges between the past and future, carrying forward innovations conceived in wartime desperation and applying them to new purposes in a changed world. Today, when aviation enthusiasts gather at museums to admire these aircraft, they are looking at more than old machines. They are seeing physical manifestations of a pivotal moment in technological history, when aviation transitioned from propellers to jets, from subsonic to supersonic, from the familiar to the unprecedented. The Luftwaffe's aircraft were among the first to make that journey, and their capture ensured that others could follow. That is their legacy. Not victory in the war they were built to fight, but contribution to the aviation revolution that followed their defeat. Well, that's it. Thanks for watching. We hope you found this video informative. The fate of Germany's advanced aircraft after World War II shaped the development of modern aviation in ways that continue to resonate today. From the Me-262 to experimental prototypes, these machines taught the world what jet propulsion could achieve and accelerated the development of technologies we still use. If you enjoyed learning about what happened to the Luftwaffe planes, make sure to check out our video, What Happened to the German U-Boats After World War II. Don't forget to like this video, subscribe to our channel, and hit the notification bell to stay updated on more World War II content. See you in the next one.